Welcome to another adventure of the New York City category theory. Emilio is speaking again, decision problems on graphs and as sheaves. Emilio, I think, has the record of speaking the most at this seminar over the years. So is it like your fifth time or sixth time? Very good. Great. Yeah. Excellent. You're always welcome. You always make things understandable. Go.
All right. So yeah, thanks, Nosen, for having me.
Yeah.
So yeah, I didn't feel like talking about my research this semester. Instead, I wanted to motivate myself to read a paper that I've been thinking about for a while. And so this talk finally gave me the kind of motivation to do that. So the paper I read was this one, Compositional Algorithms on Compositional Data, Deciding Sheaves on Presheaves, by Althaus, Bumpus, Fairbanks and Rosiak. And Benjamin Bumpus has been developing a kind of program here. So he has 3 papers with his name here, and this is kind of the third in this series. And it's about using category theory to understand algorithms, which I think is a fascinating topic. So let me get started.
Just where are these people? Or Rosiak, I heard of.
Rosiak is at NIST. Bumpus is at University of Florida. Fairbanks is University of Florida. I don't know everybody else. Lack, Sobochinsky, Perret, I mean, they're well known.
Right.
Yeah, so anyway, this is the main paper I'm going to be talking about. These two I actually won't be able to cover in this talk, but they came up a lot in my research for this. And I highly recommend both of them. They're both extremely beautiful papers. So anyway, let me get started here. So basically, what I'm going to do is talk about sheaves as decision problems. And I'm going to talk about decision problems specifically for graphs. Now, anytime a mathematician says the word graph, the first thing you should say is, what kind of graph? And this is the question I asked, and it actually took me a little while digging to really figure out what kind of graph I actually wanted to study. And so I found some stuff on the NLab. They have a page about all different kinds of graphs, and I summarized it here. So you have all different kinds of graphs, and the ones we're going to talk about today are simple graphs. So these are graphs that are not directed, that don't have multiple edges. You can only have at most one edge between any 2 vertices, and you're not allowed to have loops. And for every combination, there's a kind of graph that goes along with it, and each one of these gives you a different category with wildly different properties. Okay.
With forgetful functors and projections and inclusions between them.
Right.
And if you're lucky, some of them are actually toppling.
Yes. So.
Oh, which ones? Easy to say?
Yes. So directed pseudographs are what people would typically in category theory think of as graphs. Mm-hmm. These are directed. You can have multiple edges and loops. So if you forget about composition and identities, this is the underlying structure of categories. And the category of directed pseudographs is this category, which is a topos.
Right.
But the category I'm going to talk about now is not a topos.
There should be a long string of adjoint functors.
And one second. I mean, none of the other ones can be done like that?
Not that I know of.
That's cheating. It's like, that's, okay, fine.
So, I'm going to let graph here denote the category of finite simple graphs. So these are graphs like this. They don't have to be connected. And then I'm going to want the morphisms to be a little bit special. The morphisms are going to be graph homomorphisms in the usual sense, but I'm not allowed to collapse edges.
And you don't have loops, so you can't collapse the 2 points at both ends of an edge.
Exactly. So there's never a map to this graph if I have an edge. So that means that this is not a terminal object in this category. This category doesn't have a terminal object. Okay?
Actually, hang on, let me ask a question.
Yeah.
Because the thing you drew up there looks a bit like a loop in that it's undirected and there's a couple points and they're all connected to each other, so I can go like in a circle around them. So by loop you mean a self loop from a point to itself, or like, because that looks like
You're not allowed to do this.
Yeah.
right, but what I'm saying is
that's
you've
what you
got
mean
like
by
a loop-like
Yeah.
thing, but
This is a cycle.
okay, so you have a cycle but not a loop. Gotcha.
Yeah.
Or just relabel it column self loop and then.
Can't have edges whose source and target are the same vertex.
Okay.
Okay. So the idea of that paper that I was talking about, the category that is kind of the base category to talk about all these things is this category. And computer scientists love graphs, especially these kinds of graphs. And they encode computational problems in them. A lot of the most famous computational problems with finite simple graphs are NP-hard and NP-complete. Now, what this paper does is basically comes up with, so I'm going to say a bunch of words right now and I'll explain what they mean later. So basically what they do in this paper, this is kind of a summary of the whole paper, as an idea, is that you're presented with a computationally difficult problem, something like NP-hard. What you can do is you can study the decision problem by parameterizing it. So there's a parameter called tree width for graphs. Okay, so graphs can have different kinds of tree width, and it turns out that if you look at a subclass of all graphs, not all graphs, but the graphs, the class of graphs that have bounded tree width of let's say k, those hard problems become feasible now. And this is called fixed parameter tractable problem. Okay? So even though they're NP-complete problems, you can carve out subclasses that are more tractable. Okay? So I said a lot of words there, so let me explain what I mean. So I'll give an example of a computational problem. So 3 coloring is going to be a subclass of all finite simple graphs. And I'm just going to say graphs from now on instead of finite simple graphs. Be the class of graphs that can be 3-colored. Okay, so what does 3-colored mean? It means I have a graph like this. And I can assign colors to each vertex in such a way that no 2 vertices that are adjacent have the same color. I forgot to bring colored chalk, so I'm just going to use numbers. So I have 0, 1, 2. Now I have these are all the 3 colors I can use. I have to assign a color here, and it can't be 1. So let's say I just do 0 again, and maybe here I do 2. So this is a 3 coloring of this graph. This is a computationally hard problem. So in general, yeah?
What's the problem that's hard? Finding all the 3 colorings?
I'll say it right now.
Or to decide if
decision
a
about
graph
right?
is
So I give you
recurrent.
a graph and I tell you yes or no?
Yeah.
Yeah.
I think it's k greater than 3.
Who's K here?
I'll say n, actually. And so what do I mean when I say that n coloring is NP complete? What I mean is that I have a decision problem that says, I give you a graph, and you tell me whether or not it's n colorable.
But let's see, of course, for color theory, the only values n care about here are 3 or 4.
Yeah, so for 4 it is, it's actually polynomial, right? Where it's actually constant time, because we know
Before the algorithm is yes.
Yeah, exactly. So before the algorithm is yes.
I'm sorry, I don't think that's true. I think the 4 coloring problem was solved, but it's about planar maps. These graphs don't have to correspond to planar maps.
As I said,
yeah, the graph could have a higher genus, sure.
Yeah. Let me make a bunch of caveats here.
Yeah, right.
I'm learning this right now, so I don't know a lot about graph theory. I'm just telling you what I know.
Okay, never mind.
I might say wrong things.
Yeah, that was for a special graph called planar graph, and
Right.
basically, yeah, it depends what surface. There's a bound, but the bound depends on what's the lowest genus surface you can embed your graph in.
Right.
So,
And if you're talking about planar graphs, then you can solve 1, 2, and 3 also.
right.
Okay.
Yeah.
What's wrong with that?
No.
Okay. So now, in general, for all graphs, this problem is NP complete, right? Now we're going to bound the class of graphs under consideration. Okay? So for that I need to introduce the notion of tree width. So given a tree, T, let the integral of T be the category whose objects are the vertices and edges of T, and there is a morphism where there are morphisms like this for every edge like that. Okay. So for example, if this is my graph, then I get this category. Like that. Okay? Somebody want to say?
How do you compose?
What's the composition?
Oh, I was going to say growth and deconstruction. I
Oh.
thought somebody was going to scream that out. Yeah, so this is, this can also be seen as the growth and deconstruction, where I think of a graph, like I could take the free category on the graph, and I can take the growth and deconstruction of that, right?
What's the growth and deconstruction? If it can be done.
Don't have time for it right
Okay,
now.
sure.
But anyway,
So I take it that with this thing that you're turning a undirected graph into a directed graph.
yeah, so that's a little bit of a caveat. In the paper, they actually use directed graphs, but I don't really see how it makes much of a difference.
Well, every category has an underlying directed graph.
Yeah.
So. And this category doesn't have very interesting composition structure, so basically that's all you get.
Yeah, there's no way to compose. Yeah.
No, there's no way to compose in this graph, but in general, how do you do it?
Integral T, you have some just not a very interesting composition.
Well, I mean, you can never have a composition.
So it's a discrete category, it's a discrete set.
No, there are morphisms. Here's a morphism, here's a morphism, here's a morphism, here's a
Well,
morphism.
you can compose with the identities, and that's about
Yeah.
it.
So basically what you do is you explode out the edge, and it becomes a span.
How is like, so, well, like how is this unstraightening, or how is this visible in the construction. Like T is not a pseudo functor.
Okay, so if I think of a graph as a functor like this,
Okay.
then I take the growth and deconstruction as taking the pullback. Right?
Okay.
And in this case, you have to obviously restrict from the thing at the bottom of your chart to the thing at the top.
But one has to be more careful when they say things like this. Anyway, so, all right, so that's a category. What does it have to do with tree width? So given a graph, say, yeah, given a graph G, a tree decomposition of G consists of a functor. We continue this up here. So I have a functor D from the growth and deconstruction of T to graphs, where T is a tree, and the morphisms in the image of D are monos, and the colimit of D is G. Okay. Now, if you look in a graph theory textbook, this is not what a tree decomposition is. But as far as I understand, it is equivalent to the classical notion. So let me explain what that means. So, what do? I take a tree, like that, and then what I'm going to do is that I'm going to take the growth and deconstruction, and so that looks something like right? So every time I'm just going to push this into a span, every edge, and I'm going to map this into the graph. So for each object here, I'm going to have a graph, and so let's say I have this.
Oh,
Does this make sense? What do? For every object here, I have a graph. Okay? And then for every morphism here, I have to have a monomorphism.
D preserves monomorphisms or
Every morphism here, you
Is a
can say it in
monomorph.
multiple different ways. Let's just say they all get mapped to monomorphisms. So that means, what does that mean? It means I have, for each object, a graph, and whenever it's one of these guys in the spans, that means it's a subgraph of these two. Right? So every time I have a span, I get a subgraph that these two share. Right? And then the idea is going to be that I'm just going to glue it all together. I take the colimit of this diagram, And I get what?
3 triangles.
3 triangles. Okay. So the idea here is that you're going to decompose this graph here, G, using a tree. It's like finding a tree structure of the graph. Okay? Any questions on that?
By definition, a tree, you mean just anything without a cycle?
Connected acyclic graph.
Okay.
Right, so then in here, so it looks like to each of the edges in your original thing T, I got a graph. And then the links in the tree were telling me had to do with what I do with the gluing.
Exactly.
Okay.
Exactly.
Okay.
So this is a tree decomposition of a graph.
You're telling us what the graph width is, right?
Tree width.
Tree width. Oh, tree width.
They have a whole bunch of other widths too.
Yeah.
And let me say some terminology here.
So we define the tree, but not its width yet, right?
Yes. So I've just defined a tree decomposition of a graph G. These guys here, I call the bags.
Ooh.
The bags of the decomposition. And then these guys here, I call the adhesion. So it's getting a little bit messy. Let me rewrite it. Maybe a smaller one over here. So, bags, adhesion. Okay.
Okay, so,
And are you ever gonna get bigger than a triangle, or is that as big as it goes? Like,
You can do as big as you want.
I was gonna say, to give a sufficiently complicated graph, you're gonna have, like n simplices, basically.
No.
You can have n simplices.
Well, instead of bags you have are just triangles. I'm saying, are you gonna get bigger things, or no, because they'll all break down into just triangles, that's what I'm saying.
That was an arbitrary diagram.
Okay, yeah.
As long as I can glue it together to get G, right?
Oh, I see, so,
This thing could be absolutely huge, and each bag could be absolutely huge.
right now, a stupidly
I
trivial
think
thing
we're-
where I'm going
The
one
whole
bag
thing-
into the original
yeah,
graph.
the whole thing could be one bag also. I could map a tree as a single point. That's also a tree.
I see, because it's not decomposition. It's not a unique
It's not
thing.
unique.
It's just like any old thing that I can glue together that comes out of something that has tree property.
That's right.
Okay, gotcha.
So I
This
call,
one is just particularly tricky, yes.
yeah,
The integral teeth is, so the integral teeth in this diagram category,
Yeah.
for gluing these things.
so the width of the decomposition is, I look at all the vertices in my tree, and I take the size, the biggest bag, and I subtract 1. Why do I subtract 1? Because I want trees to have tree width 1. And every tree has a really simple tree decomposition where every edge becomes a bag. So that means that the largest bag here has 2 vertices, so the tree width is 1.
Okay, so again, you can, depending on the decomposition, you might calculate a different width.
That's right, that's right.
Yes.
So this decomposition has width 1. And this is how I'm probably going to draw decompositions from now on. It's a little bit easier. Okay, and then tree width is kind of the obvious thing now. tree width of a graph G is the minimum of the width over all tree decompositions.
So in particular time, your triangles would not be tree decomposable further.
Say it again?
Well, your triangle wouldn't be, you know, and wouldn't have, has no non-trivial tree decompositions, for instance.
I think you're, well, I mean,
Something better not, otherwise the tree width would always be 1.
well, I mean, yeah, I mean, there's trivial ones though, right?
But I'm saying non-trivial ones, yes.
Yeah.
That's sort of like a prime, you know, some kind of prime in this game. They can't can only decompose it trivially.
Well, there's always a tree width,
Yes.
right? But it's not 1.
No, I think the question that he's asking is, if I have if I look at all my trees, I can enumerate which trees have no, like, decomposition, or which graphs, I guess, have no spanning trees that are, you know, that are, like, that trivialize, right? So, so in other words, right, like, I give you one, and you might say, well, this has, you know, 8 points in it. You might say there's no way to chop it up into one piece that has, you know, any less than 8 points. So the minimum width is the size itself, and those would be the quote primes.
Right, so by counting, presuming this is not, if this was always, it would be not very interesting if the answer was always 1.
Sure, yeah.
And I would guess the triangle is the first example of something where it isn't 1, and
Exactly.
which is exactly.
And you can't just, like, draw a line around each of the lines, a circle around each of the lines in the triangle and say that's a decomposition.
Right. Yeah.
Right.
Exactly.
I get a spanning tree, but that's not the whole triangle.
Right. Okay. So,
Does a regular combinatorials have a definition of a tree width?
yeah, and it's I mean, it's equivalent, but they just describe it differently.
All right, so is it easy to say what they say?
I don't remember exactly what they say, but it's this picture. All right. So here's the idea. So suppose I have a graph, right? Suppose I have a graph G with 1,000 edges, and I want to solve some computational problem on this big graph, right? But say I only know how to solve it in exponential time, and I can only solve my problem, call my problem P on G in exponential time. So that means that it would take you know, 3 to the 1,000 time, which is prohibitively expensive to compute on the whole graph. The idea is going to be that if I can take a graph and I can find a tree decomposition such that the bag size is small, what you do is that you solve it on each bag. So using a tree decomposition with let's say K, then it looks more like you're solving 3 to the K times 1,000. And this will be significantly better runtime than that.
Big time.
Right? But that means that you have to restrict to those graphs that have tree width less than or equal to K. That's the idea. So now, enough philosophy. Let's get into the main theorem here. So I'm going to state the theorem, and then I'm going to explain what all the words in the theorem mean afterwards. Well, not all of the words, but most of them. So let C be an adhesively co-complete complete category equipped with the coverage JDM, then we have, this is the main theorem of the paper, Althaus, Bumpus, Fairbanks, Rosiak. It says, if X is a JDM sheaf, then and A of X is an algorithm that computes X of C in time alpha of C for all objects C in the category, then there is an algorithm that decides if X of C is non-empty, there is an algorithm that that given a decomposition D, decides if X is non-empty in time O of max X here, alpha D of X where kappa is the max of the bag size. All right, so let me explain this really quickly, and then I'll explain what each term means individually. So first of all, think of C being an adhesively co-complete category as a category with really nice colimits. And the coverage is going to be, imagine like a covering family as looking something like this. Okay? So I have covering families and they look like these maps coming from the co-cone. Okay? Then if I have a sheaf with respect to this coverage, that means that if I know how to solve, if I know how to compute X of C in this amount of time, so say this is exponential time, then there's an algorithm that if I'm given a decomposition, it can tell me whether or not this decision problem is true or not, whether or not this is empty, in this time. And what you'll notice is that this here is like the tree width, okay? So this is saying, what I can do is say I have an exponential algorithm, and I only know how to solve my problem in exponential time. Then I look at the maximum bag size of my tree decomposition of a graph, and I solve it there on the bags. But then, so say this part is exponential, okay? But this is bounded because I assume that I have like some decomposition, I'm taking a maximum here. And then this is the actual size of the graph. So this is the linear, so it's linear in the size of the graph, right? And then you have this extra term, which I'll talk about during the proof.
So I guess the point is that since you have a sheaf, if I can solve it on the bags, then I can just glue the answers back together to get the answer for the original graph.
Exactly.
Cool.
Okay.
It's extremely simple.
Nice.
But what happens if you don't do a tree decomposition? Suppose you have one single cycle.
Yeah, then you have to solve it on the one.
Well, then this is trivially the case.
That's correct, that's right. Absolutely. I'm just goosing you. I mean, I'm just asking a question.
Yeah.
That's what I meant to say.
All right, so I'm going to explain a good chunk of this, but not everything. So let me give a definition sketch here. So we say a finite diagram is submonic if all the morphisms in its image are monos. We say a category C is adhesively co-complete if it has colimits of all submonic diagrams and taking pushouts of spans that look like this, behaves like it does in set. What I mean by that is that a category is adhesive if all pushouts along monomorphisms are Van Kampen. And then adhesively co-complete is an adhesive category that furthermore has colimits of all submonic diagrams. And you can read this paper by Lack and Sokochinsky, just called Adhesive Categories, to learn more about this. Adhesive categories are really fascinating because they give you a lot of powerful tools for rewriting theory.
Oh, okay.
But that's all I'm going to say about that. And here's a fact. Graph is adhesively co-complete. All toposes are adhesively co-complete. Another definition. So, given, I'm going to say,
Going back to your thing, so it's not, I guess, just graph in the sense of the directed graph, but the simple graph, you're going to use that category, the subcategory will also be adhesively co-complete.
sorry, say that again?
Well, in addition, because it's a topos, but only directed pseudographs or topos, but you have simple graphs with subcategories, so I take it that one's also adhesively co-complete.
This is not a subgraph. This is not a subgraph, but you're right. This
Well,
is
subcategory of, I was saying that. Well, I'm just saying that you're using simple graphs, not the ones which are topos. So that category is also adhesively co-complete. I was going to check.
That's right. Okay. So now what I'm going to do is generalize from this category to all adhesively co-complete categories. Okay. So an adhesively co-complete, given an adhesively co-complete category, a structured decomposition of an object seen in C is a functor like this, such that the colimit of D is C. Okay? So this is generalizing the case of tree decompositions to any category with nice enough colimits. And then a morphism between structured decompositions looks like this. Okay?
Where T is what?
A tree. I think in the paper they actually might just say any graph. Yeah, so maybe T should just be a graph.
Yeah, that was going to be my question too. I don't understand the theorem, but I vaguely have the idea maybe. And then the question is...
This theorem only holds for
Yeah.
trees.
But that one also has to only hold for trees.
So,
right?
let me. That's a good point. So here, this only holds for trees. They have another theorem that's for a more general class of graphs, but it's a harder theorem, and I don't understand every part of it yet.
But it's tree-like. It has to be tree-like, otherwise they'd have solved a whole bunch of problems that are famous. I'm sorry, I happen to know that. Okay, I'm sorry.
I
should not have interrupted.
I don't know how to respond.
Understand, but it looks to me that
Yeah,
way.
you can look in the paper.
Yeah, absolutely.
So then we let dm be the category dm of C, be the category of structured decompositions in C. And now I'm going to define a coverage. And when I say a coverage, you can think of growth and deep topology. Every coverage is like a collection of covering families, and every coverage generates growth and deep topology. Okay? So define a coverage JDM on C by saying that the cocomb of a structured decomposition is a covering family. So I said this in words before. So you imagine you have some object, and you have a whole diagram of sub-objects, or maybe not necessarily sub-objects, but you have a whole bunch of objects above it, and the colimit of this diagram gives you that object. So that means you have a cocomb, so that means from every object you have a map to it, and that's a covering family. Okay, so once I have a coverage on a category, that means I can define sheaves on it. So now I have a category and a coverage. So I want to talk about sheaves on this. So let's take a look at an example. I'm going to take the category of finite simple graphs and the coverage given by structured decompositions. Now I'm going to give an example of a sheaf. So first of all, let me just write over here. There's a bunch of very famous graphs called the cliques, and they look like this. Right? So this is what I call K0, K1, K2, K3.
The one skeletons of simplices.
I was just about to say that. The one skeletons of simplices.
They're fully connected, right?
Yeah. So it turns out that there's a bijection between n+1 colorings of a graph G and morphisms in the category here. And the way you can see that is let's say I go to, I don't want to do it like this. So say I send this triangle, like I have A, B, C, D, 0, 1, 2. I send A to 0, B goes to 2, C goes to 1, and then I can send C, D to 2, right?
This wouldn't work unless if you worked in the general category.
If you worked in the general category where you could collapse edges,
Right.
then you could do anything you want,
Right.
and then you wouldn't have this result. Exactly. So this only works when you restrict the kind of morphisms. And this is a sheaf.
And what's a sheaf?
So I'm always gonna work in thin set rather than set. But you can think of it in set and say it's a sheaf, right?
What's a thin set? You mean the
Finite
skeleton?
sets.
Oh, finite sets. A thin set, I didn't understand.
So let this be the functor that takes a graph G and just maps it to K. This is a fact and it's easy to check. This is a sheaf. And it's really easy to think about. If I have a graph and I look at these two subgraphs and I can color each of them such that the coloring agrees on the overlap, then I can extend the coloring to the whole thing. Right? So this is a sheaf. Okay, so this is an example of the kind of thing we're looking for, and this is going to work for our theorem.
Yeah, don't erase the theorem.
Don't erase the theorem? That's going to be a little confusing, but okay.
I'm sorry.
Maybe I should have written it over there.
No, because you're going to have to come back to the theorem and restate it.
Well, that's a good example of why if you're not planar right away. Then, yeah, just take that and cleave, and then obviously it's going to be all that most colorful.
Take the end sheaf and click on what?
Well, yeah, because you could just, if you don't have to be planar, right, I can have 12 points, each of which is
Right.
connected to every other point, and then clearly I need 12 colors to.
Right. The end click needs end colors.
Yeah.
Yeah.
And also about the statement of that theorem, like I guess, like how strong is it? Like
This?
like it just as they asked earlier, it can't be that you just prove that V equals P.
No, no.
So of course, like how strong is it?
So this is like a basic idea in parametrized complexity theory, just like the modern iteration of computational complexity theory, where you parameterize your decision problems, so you can find NP-complete problems that are fixed parameter tractable. So theoretically, they're still NP-complete, but when you restrict it by this parameter, and you only look at this parameter and less than that, then it's computationally feasible. So this is why things like SAT solvers still work. Like SAT solving is NP-complete, but somehow, people SAT solve all the time with their computers.
But also remember, if you use this, I need to know a tree composition into things with small width.
That's right.
We haven't said how you get, where that comes from. You see that's
Right, so
why.
what's the complexity of calculating a tree?
That's right.
We would do
Yeah.
P versus NP easily if if we had a homology theory that
Yeah,
beyond
yeah.
H1, I think. So,
So now, what we're going to do is stare at this diagram. I didn't give myself enough space, fortunately. Let's see here. Okay. Okay, so let's stare first at this left-hand diagram. Okay, so let's stare at this left-hand diagram. What is this saying? I have a structured decomposition of an object, and then I take its colimit, right? So I'm going to glue all my subgraphs together and get an object, and then I'm going to evaluate my sheaf x on it. Then here, what I'm going to do is I'm going to consider my structured decomposition, and I'm going to evaluate my sheaf on each piece. And then I'm going to take the colimit. But in this case, it's opposite, where I'm actually taking the limit, okay? Because the sheaf is contravariant.
Yeah.
This diagram commutes because
Divide and conquer.
divide and conquer because x is a sheaf.
Yep.
Okay?
Right.
Somebody could say x is a sheaf because this commutes. Right?
Sure.
Right? So it's equivalent to x being a sheaf. This one's a little bit more difficult to explain. So let me say it. What's this guy? It's this. Okay, so basically the idea is we want to find a way to make this big diagram, this big outer diagram commute. So the first thing you would think of doing is the following. I want to do my divide and conquer algorithm. So I want to evaluate x on every little piece. I want to see if every little piece is empty or not, and use that to decide if x is empty or not on the big thing. Right? So imagine that A here doesn't exist, and this is just this functor. That outer diagram is what you would think originally as like a divide and conquer algorithm. This functor dec tells you whether or not a set is empty or not. Okay? So dec takes a finite set and gives you 0 if it's empty and 1 if it's not empty. Now the problem is that that diagram that you would naively think doesn't commute. Okay? What you have to do is you have to augment it with this functor A. And this functor A is where all the complexity of this paper is. Okay? So this theorem, the whole proof basically comes down to understanding this A. This A is like a pre-processing thing. So once we prove that this A exists and this thing commutes, this gives us our algorithm, because it says compute x on all the pieces, do a pre-processing thing, check if each of the pieces are empty or not, and then join them all together and see if that's empty or not. And that'll tell you whether x is empty or not on the big thing. Okay?
So going along the top somehow tells you if it's n-colorable or not?
Yes. So if I have a graph,
Yeah.
say C is graph,
Yeah.
I take x, which is n coloring,
Right.
and I evaluate it on that graph, and then if I see if it's empty or not.
Right.
If it's not empty, then I know my graph is n colorable. So that's literally the example I'm going to give right here. So this is like dx dy dz df to apply my sheaf to each of these pieces. And what I end up with is
Conveniently have my pieces here on the conveniently K2s.
Yeah. So I have this map going this way. Now when I apply my sheaf, it's going to go the other way, where I take a 3 coloring on this thing and I restrict it. And then, right? Well, you know, let me just write the whole thing here. I'll just do it one more time. So that diagram has become this one. Okay. And so this functor A is going to do the following. It's going to say, these things are too big. These sets are all too big. I want to take a subset of each one of them. Because there's a whole bunch of 3 colorings here and 3 colorings here that when I restrict them don't agree. I only want to restrict to those where they all agree. I want to get like a matching family. So what I'm going to do is I'm going to take the limit of this, limit of 3 coloring of D, and I get all of these maps, right? And then what A is going to do, A is a functor that takes a diagram that looks like this. They call them structured co-decompositions because of this op here. So this is a structured co-decomposition in finite sets. So I have a bunch of finite sets and then these maps, right? And I'm going to give you another one. And what's the other one going to be? Well, I'm going to take the image from all of these, right? Because what does the limit do? The limit takes the product of all of these and takes the subset of all of them such that they all commute, right? So then what I'm going to do is I'm going to take the limit, I'm going to take the image of each of these maps, and I get a new diagram. And this is a new diagram here, okay? So this does like a pre-processing thing, where it says, all of the 3 colorings are too big, I only want to look at the ones that actually could be in the limit. Okay, so then I'm gonna, how much time do I have?
As long as you want. This is very understandable.
Okay.
So we're, I mean, we're an hour in, but.
Okay, I'm gonna state this lemma and I'm gonna give like a sketch of the proof and then I'll be done.
But then you're gonna go through the theorem again.
Well, the theorem is gonna follow from this.
No, you're gonna go through the statement of the theorem.
Oh yeah, okay. Yeah, I'll go through the statement.
Please.
So there's an algorithm which computes that functor A on a decomposition in time O kappa squared E T, so D is a functor finite T as a tree. So what is this saying? It's saying I'm going to be able to take this thing, and I'm going to be able to do this pre-processing, and it's going to depend on the maximum size of the bag. It's going to be quadratic in the maximum size of the bag and linear in the size of the graph, the size of the tree. So I'm going to prove this, because you should always prove one thing, right?
So you won't prove the whole theorem, but at least we'll prove the lemma.
Prove the lemma. And actually, from the lemma, the theorem will follow immediately. So, the first algorithm, I have to actually do two algorithms here, but they're actually really easy. So the input to this algorithm is a structured decomposition, like this, and an edge in my tree T. And then what I'm going to do is two things. I'm going to compute the pullback So remember, this is coming from here. When I have a structured decomposition, I get a diagram like this, and I can take the pullback. Call this pi of x, pi of y, f of x, f of y. That's step one. And step two is let dE be the decomposition which agrees with D everywhere except at E, and there it's going to look like this. So what's it doing? I take a structured decomposition, so you can think of it as a diagram of finite sets like that. I'm going to take an edge in my tree. I'm going to take the pullback of this span here. I'm going to take the image of that pullback. I'm going to get a new span, a new cospan here, right? And everything here will be unchanged. I do this for every single edge until I finally get a new decomposition. And the claim is that's the same thing as doing the limit all at once and taking the image there. Can't erase this, right?
No, sorry.
Is that clear? Sort of?
You bust apart things until you can manage them. You want smaller and smaller until you can.
Right. And then 3 I'm going to return. Okay. And now algorithm 2, so I'm going to use that as a subroutine. So here the input is going to be structured decomposition. And a list L of the edges of T. And then I'm going to do a very simple algorithm that says if L is empty, return the decomposition, because that means that the tree is empty, so the decomposition, I'm not doing anything to the decomposition. Else, what I do is I split L into its head, E, and the tail, L prime. So what do I mean by that? I have a list, and then the head is the first thing, and the tail is everything but the first thing. So I do that. And then finally, I let DE be the output of algorithm 1 on the input D. So what's this going to recurse? It's going to take a list of the edges and it's going to recursively apply algorithm 1 to every edge. Okay? So very simple algorithm. Now, the mathematical content here is to say the following. Mathematical content is to say that if I have a diagram like this, and I take the limit of this diagram, that's the same as if I took pullbacks.
Break up computing the limit, first do pullbacks, then the...
Now, it turns out that knowing when you can do this has actually already been understood. It turns out that when you have a simply connected diagram, you can compute its limit using only pullbacks. And that's this paper here, Simply Connected Limits by Perret. Okay? So I had to do a little bit of digging, but I saw that. Unfortunately, even though that paper is really nice, it doesn't actually tell you how to do it in the finite case, like how you actually do it. I mean, it's pretty simple, but because he's dealing with a much more complicated class of diagrams, so he has a pretty high-powered procedure on how to do it. But anyway, that's the mathematical content there, and this algorithm is just implementing that. I should have said here, recursively call algo 2 on inputs. D, L. Okay, so now we're going to prove the lemma, right? So that says that this algorithm has running time that. So first we're going to prove correctness. And we will induct on the size of the tree. Okay, so if the base case then it's easy to see that A will do nothing. And now the inductive step says, suppose this algorithm is correct on trees of size n, is correct on trees of size n, let T be of size n plus 1, choose an edge in T. Once you choose an edge in T, you're going to separate your tree into two subtrees. I have T1, I have X, and I have T2, Y, and E. And the whole thing is T. Okay? And then I let D1 be D restricted to the subtree T1, and D2 is D restricted to T2. And then what I end up with is I have D of this. So I have DE, I have DX, DY, and those look like that. And this is a part of a big diagram, which I call D1. And this is a part of a big diagram called D2. Okay? And then what I do is I take the limit of these two. And then I take the pullback. Okay? And then the claim is that P is the limit of the whole diagram. Now, why is this true? Suppose I had a Q here and maps like this. Then I would have a map to the limit over this diagram, and I have a map to the limit over this. So I have a cone here, and I have a cone here, such that whenever I take all those maps and I go to here, and I go here, they agree. That means I have a cone on the whole diagram. So therefore I get a map to the limit, uniquely. But that means that this thing is a pullback. So this is the limit of the whole diagram. Okay? So now, all I have to do is remember that this functor A is the image of this limit. So that means that I can do the following. Because A dy and A dx are the image of this limit. So you call this P1, P2, lambda 1, lambda 2, and finally we can take this pullback here, and I promise I'm almost done. I get a map U here, and you can check by yourself that U is an epi, because these are sets, and this thing, these two sets are images of the limit cone, and this map just takes both of these pieces. Those things are already going to be in the image, so this function is a surjection, which means that if I have this, then I know that lambda I pi equals pi iu. So then the image of lambda I pi equals the image pi iu, which is the same thing as the image of pi I restricted to the image of u. But the image of u is everything, since this thing is surjective. So that means this is just the image of pi I. So that means that the image of these, the image here, which is A, and the image here is the same thing as these two. So that means when I took the pullback here and I took the images there, that's the same thing as taking the image of the whole limit. Okay, and I'm finishing up right now. So that shows So that proves correctness. And then the running time is really easy. Computing pullbacks takes time O kappa squared, where kappa is the max.
You have it over there, you have it over there. dx.
Why is it quadratic? Because I take two sets and two functions going into something. The worst case scenario is that they always agree, in which case I'm taking the Cartesian product, just kappa squared, right? And then I recursively call algorithm 1 et many times. That's how you get this running time. Okay? And then for the theorem, finally, what I do is I just take my algorithm, I run it on the bags, that takes this amount of time, and then I do the algorithm, and I check the resulting thing to see if it's empty or not, and I'm done. That's it.
So let me just say, this is beautiful for three coloring problem, but how general is this? I mean, the three coloring problem is somewhat geometric, and so it fits in very nice with this.
Yeah, so the point is anytime you can just say your decision problem is a sheaf, then you automatically get this.
So I guess the question, let's say during paper I have examples other than this geometric one of, what are examples that they have of such decision problems?
Vertex covers, independent sets, all kinds of graph theory.
So basically, again, when they graph things, and usually if you think geometrically you'd expect the sheaf, it probably will be.
That's the hope. But the point is that this kind of thing is proved all the time. Yeah. So I talked to Benjamin Bumpus, and he was explaining a little bit like how he came up with this idea. The thing is that like graph theorists prove this kind of theorem like over and over and over and over again for different kinds of graphs with different kinds of bells and whistles attached, and this idea is just used over and over and over again, right? So the point was he saw this going on over and over and over again. He said, why can't I just do an abstract?
So this is the master theorem.
This is the master theorem for a whole bunch of results. And they're all proved in just the same way.
Yeah.
Okay? But every time you have to imagine how difficult it must be to like look through all of the like careful details of everything. Right.
As opposed to just check that the thing is a sheaf.
Exactly.
So this holds for different sorts of graph types as well.
It holds for like this, adhesively co-complete is not a very big condition. There's a lot, every topos, so that means that every time you have like any kind of data structure you can write down as a presheaf category. So like graphs, hypergraphs, relation, I think if you model databases in a certain way, you can do it. All different
But you need a
kinds.
generalized notion of tree decomposition and tree width, right, for...
That's the structure decomposition.
Right. It's just using that diagram category of his.
Right, so that's the generalized width notion.
I think that I know
Oh, you mean
a version for
databases.
databases.
Okay.
Oh, I see what you're saying.
Anyway.
Like if
For
I
a category, what I mean,
Yeah,
So
so graph, I know what a tree is, or like...
Yeah, this
I
algorithm
know what
works
the size of the graph
specifically
is.
because you have a tree, like sort of a
Exactly.
hierarchical tree type of
Yeah,
structure.
yeah,
Are there
this
any
wouldn't
results
work.
for more interesting
Yeah.
decompositions? Like
Yeah,
if you had,
so
yeah.
the actual main theorem of this paper is not this. This is like the secondary result to a bigger result, which
Okay.
talks about a more expansive class of graphs. So I think it's any graph, but then you have to have like an extra piece of data. I'm kind of forgetting now.
Well, let me suggest one version of the improved theorem. If you go in a cycle in the schema of a database, then if you can control the complexity of propagation of constraints, you'll get some theorem like this. But you have to have that as a separate thing. I'm just conjecturing. I mean, maybe I misunderstood it. But for the simplest case, for the database where you have an acyclic database, that's a tree, in some sense. There's a unique path between tables. There's a way of defining tables, and as I mentioned, Graziella Cicciolnischi proved some theorem in '93, and then she recently has noticed the connection with Bell's theorem. Anyway, just you know, I think it falls under this, but I'm not sure.
Yeah, so you can find the more complicated theorem in the paper that uses not just trees. But this is the only thing that I could understand.
This is nice.
If the converse were true, that would, I think, prove that P is not equal to NP.
Okay.
But namely, you have to have an external bound on the complexity of propagation of constraints. This is all conjecture.
Yeah.
But presumably that's true.
But the tree hypothesis here is so important. Like this, none of this works if it's not if it's not a tree, because you need a simply connected limit.
Well,
which is very interesting.
You only get a presheaf in my case. If it's not a tree, if it's not an acyclic database, you just get a presheaf, which is completely different for this kind of stuff from a sheaf, because you break it up and then you're not done, because like you loop around and it's not good enough. Then you have to then consider, like, you know, well, this says yes, this says no, and what's his name? Oh, sorry.
Yeah, but if you had more interesting,
Abramsky.
like more interest, if you were able to have more
Abramsky.
interesting sort of meta structures besides trees, you might be able to get away with smaller bag sizes.
Yeah.
That's what I'm thinking.
Exactly.
So it seems like that's where the meat would be.
But this is already very, very powerful.
It's freaking.
No, this is slick, because it's so
extraordinarily
there's so many
impressive
recursive CS algorithms that seem like their versions of this, right? This is
right. So the hope, Bumpus's kind of mission here is to develop, you know, these kind of meta theorems for algorithms, so we don't have to reinvent the wheel every time we want to do an algorithm on a different kind of data structure.
Yeah, what I was saying, you know, the intuitively means that's basically a prime factorization. I use this tree thing as a way of factoring into primes. And so you're saying that, yes, if you can solve it on the primes, then, you know.
Yeah.
Which then makes an interesting question, like for these trees, you know, first of all, how many of those are there? Of the indecomposable ones.
Mm-hmm.
I was just reading something in Quantum magazine that was like very similar to
Oh,
this.
yeah?
I literally can't remember. I'll forward you the link. But
Yeah.
it was like some CS people came up with some result that was like anyway.
So I googled up a quick thing because I was curious about this, which I'm sure the paper talked about, but I just don't think you mentioned specifically, which is like that. If I fix K, I can determine a tree decomposition in K. Like, so if I've got a graph, and I say I know this graph has a 3-width decomposition, that's linear to calculate that decomposition.
Exactly.
But it fails. It just goes like if it doesn't have one.
Yeah.
And so that's sort of the trick, because I don't need actually, that was the request I had, is do I need to come to the table with a decomposition already to make it work? Did I push the work into the decomposition? The answer is no, but only if I fix the K ahead of time.
Yeah.
If I say, what is the width of the decomposition, and then let me do it, then I'm stuck back in NP land.
Right, yeah, I think I misspoke actually,
Yeah.
because finding a decomposition, I think, you said it was linear, right?
It's linear for any given fixed
For
K.
a fixed K, it's linear. So it's actually, yes, you're not actually moving the difficulty around, exactly, yeah.
But if I don't fix the K,
Then
somehow there's like some little trick, and then all of a sudden, whoop, I'm in NP land.
Exactly.
Right, so again, trying to find it, which sounds plausible, yes, finding that, knowing does this graph have such a K is a hard problem.
But yeah, but like, so you just fall off the end of the world in the algorithm, I guess, if it doesn't match this assumed K.
Wait, what's the algorithm for finding a fixed width decomposition? Like, how would that even work?
Yeah, I don't know.
You try them all.
I don't know, I can imagine
I can
that
tell
if
you
you
try them all
presume,
exhaustively. I don't think there's anything that's better.
right, you're just gonna presume that every clique will be at least, at most n size, so you can be very efficient. And like almost probably it's a greedy algorithm.
Right, if you restrict
Yeah.
locally the degree of connectivity, then you can force it into this, but
Because then I can use choice basically and say, oh, if I've already added this many things to this, then that's gotta be complete, I'm done. There can't possibly be anything else, I don't have to backtrack.
Sounds
That's right,
plausible.
the whole point of this is you can limit backtracking.
Mhm.
And that's the tree-like thing, whereas if you have a cycle, and Samson Abramsky and his crew wrote this about quantum stuff in 2012, I think, I forgot.
It's like a parser, like if I know that I've got a fixed grammar, right, with like two
Yes.
look ahead, then that's easy.
That's right.
But if I can add look ahead to a parser as long as it's fixed look ahead.
Yes.
But if I have arbitrary look ahead,
Absolutely.
then I can just like immediately fall off the edge of the world.
And let me just mention, when I first heard of K, what is it called, K parameterized complexity, they gave examples in the first papers, and like, the thing is linear, and then, but what are the coefficients? The coefficients are very, very, very large to the I. I mean, they're not the best, but like they didn't fit in the page, for example.
Anyways, I think we should thank the speaker again. We could,
Thank you.
Grows, it grows fast. Yeah.
you're always welcome to give a talk, whenever, once a semester at least.
Every semester.
Every